Okay, so we've been talking about redox reactions, and the main reason we're having this unit is so we can lead to these concepts of a battery. So to start out, I'd kind of like to review, and I would always encourage you to draw this little redox table I like to make to help us organize and retrieve all this information we're going to be using. So a redox table, I always have redox, and this just helps us organize some of the things going on with the reduction side of this and the oxidation side of this. So first off, remember Leo the lion says Gur. That means the loss of electrons is oxidation. So here we got lose electrons. And the Gur, the gain of electrons, is a reduction. Now, also, I like to always include the arrow to identify which direction these electrons are flowing. This is really to help us tell what's going on in this battery. So if they're being lost here and gained here, the arrow would be going in this direction always, from the thing being oxidized to the thing being reduced. Okay, now from last class we talked about these half reactions, that a redox reaction really involves two half reactions, and I also like to get a little half reaction column or row here to show us what's going on. So when electrons are being gained, that means the electrons would always be found on the reactant side of the half reaction. So when things are being gained, they're found on the reactant side of the half reaction. When electrons are being lost, they would be found on the product side of the half reaction. Now, we're saying that electrons are being gained and lost. So what's going on here is that, let's say I have a metal. This could just be like metal X. And let's say I have another metal Y. Now these have to be two substances, elements, and they don't always have to be metals. You know, it could be a solution or it could possibly even be a gas, and we're not going to get into that, but let's just say it's two elements here. Now if one of these has a tendency to lose electrons and one of them has a tendency to gain electrons, then we could connect these two metals with a wire. And then we could connect them with something that will allow ions to flow. Now we would also have to connect these in some sort of solution. So I'm just going to draw two terrible little beakers here. So these would be beakers that would allow things to flow. Now we're going to connect these with something that will allow charge to flow. This little connection here is called a salt bridge. So again, this connection here is called a salt bridge, and we have two elements here, one that has more of a tendency to gain electrons and one that has more of a tendency to lose electrons. And they're connected with a wire here. And if we are allowing for this to be connected and this to be connected, we can now cause electrons to flow, and that's essentially electricity here. Okay, now a couple things. There is an ox. There is also a red cat. What do you mean there is? I don't know. There's just an ox. And there's a red cat. If you remember earlier in the year, Katie, I think you were one of the people always mentioning this. I had those pictures up in the room from the beginning of the year with an ox and then a red cat. And I made sure it wasn't a red ox. Don't ever say red ox. This means the oxidation half reaction is going to occur somewhere called the anode. So an ox. This is just the electrode or the element here where the oxidation half reaction is going on. And then what is this here? Well, the reduction half reaction electrode is just called the cathode. So we have a red cat and an ox. Now, which metal here is going to be the anode and which one will be the cathode? Well, we would have to know how likely they are to gain and lose. Which element would rather gain, which element would rather lose. Now, to know that, you're going to use a chart called a standard half-cell reduction potential chart, or reduction potential chart. So I provided that for you, and here's a long list here. So we have You notice that some of them say E here. This is their standard reduction potential. On their own, these mean very little. It has to kind of be going with something. So it looks like lithium +1 is gaining an electron to form lithium, but that's a -3. All the way here on the bottom, we got fluorine gas reacting with 2 electrons forms F2-, and that's a +2.87 here. What this means is that things that are very positive are the things that want to gain. So these things down here are the things that want to be reduced. So the most positive thing is the thing most likely to be reduced. It wants to gain. If we think about the location on the periodic table, I hope it makes a little sense that these fluorines are things that like to gain electrons. Okay, down here, or not down here, up here, lithium. Things with negative numbers are things more likely to be oxidized. So things with the highest number are most likely to be reduced, and things with the lowest number, the most negative number, are more likely to be oxidized. So going back to our standard reduction potential chart here, I would just now like you to write down that whatever has the highest, even if it's negative, I guess, whatever has the highest standard reduction potential would always be the thing being reduced, and whatever has the lowest standard reduction potential is always the thing being oxidized. And if we want to calculate the voltage that could be theoretically produced, we take this number, this voltage, and then we subtract this voltage. Now if this is really high and if this is really negative, remember when we subtract a negative, that is going to equal the highest voltage possible. And then electrons will be flowing in the circuit. Okay, I kind of went through the explanation already with that discussion. Let's check out this practice problem about this practice little battery or this practice circuit. For the voltaic cell shown below. So a voltaic cell is one that's creating a positive voltage. It means it's going to create energy when we hook it up. That's all. Which element is gaining electrons? So look down here. I have aluminum and I have gold, it looks like. So, and you guys, this is actually make that a +3 there for this to work. So let's check this out. You know what I like to do? I like to fill out a redox table for a problem like this. And I know it becomes a little redundant, but I don't care. I like to always fill it out. This is the reduction is going to be gaining electrons. The oxidation is going to be losing electrons. The electrons will always flow from this to this. The half reaction will have the electrons on the left. This half reaction will have electrons on the right. The reduction half reaction is always called the cathode. The oxidation half reaction is always called the anode. Remember, an-ox and a red cat. This is always the highest value, and this is always the lowest value. Now, let's look on that standard reduction potential chart and find Al3+. So it looks like Al3+ is right here, -1.66. I'm just going to jot that down right here, just for -1.66. And then it looks like my Au3+ here on the bottom is a +1.5. So this is a +1.5. So now which one of these values is higher? Well, the Au is higher. So that means the Au would go here and the Al would be here. That means the gold is being reduced and the aluminum is being oxidized. And if we want to calculate the voltage, we would do 1.5 minus a -1.66. for a total voltage produced of 3.16 volts. Now, let's check out, we can answer any question that someone would probably ask about this little battery here using our redox table. So above, which element is gaining electrons? Well, it looks like the gold is gaining. Which element is losing electrons? Well, the losing is the aluminum. Which element is being oxidized? Well, the oxidized is the aluminum. Which element is being reduced? Well, the reduced is the gold. Write the two half reactions. Now remember, we practiced this last class, and here we need to just think about the charge here. So Al3+. So for the reduction half reaction, the gold, so I'm going to get gold here. The gold is being reduced. And I want us to think about what side the electrons are on. They're on the left side there. So how many electrons would go with a +3? 3 of them. So this would actually be Au plus 3 electrons is turning into Au. Remember, when we're being reduced, the electrons are always on the left side, which would mean that would have to go with that positive charge to kind of balance things out here. Okay, now what's the oxidation half reaction? Well, in the redox table, it says that oxidation half reactions will always have the electrons on the right side of the arrow. Now, how many electrons would kind of balance out a +3? Well, 3 of them. So this time, we're going to get Al plus 3 electrons on the right, and the aluminum would go on the left. Okay, now label the anode and the cathode. You know, because we have our redox table, the anode is the aluminum. Here's your anode. And we're going to be using this in the lab. So again, in the lab, just look up the lowest standard reduction potential, and that'll be your anode always. And then it looks like we have a red cat, so the cathode side is the reduction side, would be the gold. So here's our cathode. What voltage could be produced? Well, again, 1.5 minus a negative 1.66 is 3.16 volts. Now this is kind of a weird question, but think about this. Redraw the cell to show what it would look like after a few days have passed. Now I want you to look at these half reactions, and I want you to think about this question and then pause the video just for a couple seconds. Are we making gold, or are we making aluminum solid? Which one of those substances is being made? Solid gold or solid aluminum? You know, the opposite of the solid would be the ion. Okay, you see we're making gold. So this gold one would be like coated up with more of it. You would be making gold actually, but remember, it's not free gold. You're making it from gold ions, which are just as expensive as the gold proper. So you're making gold, and what's happening to the aluminum? The aluminum metal is being used up and turning into aluminum ions. So this would be like withered away in a few days, and like eventually I guess that aluminum metal would be, I guess theoretically, all gone. You know, if you had enough ions in here. And down here below, I just want to mention one more thing. The porous barrier means charge can flow. This is kind of our salt bridge right here. Okay, over here for practice 2 problem. Can you try this one on your own first and then check the answers? So pause the video and try this, and then we'll check the answers. Okay, so here we go. I don't like to go through these questions. I just want to fill out a redox table, and then I have my answers waiting for me. So a redox table is reduction oxidation. The reduction is always the gain of electrons. The oxidation is always the loss of electrons. The electrons will always be traveling this way. The half reactions will have the electron on the left and the electron on the right. Here's gained, here's lost. The reduction side is the cathode, the red cat. The oxidation side is called the anode, that's anox. We're always going to put the higher value here and the lower value here. And then we'll subtract the voltages to get the total possible, or we'll subtract the standard reduction potentials to calculate the voltage that could be produced. So let's look at our little electrochemical cell here, our voltaic cell, which is really just a battery, essentially. So I have Ag and Ag+. I'm going to look up on my thing. Ag and Ag+, it looks like have a standard reduction potential of 0.8. And then iron 2+ is all the way up here. That's a negative 0.44. Any of these units would be volts, I guess. Voltage is just a measure of really electron flow potential, I suppose, the ability for electrons to flow. Okay, so which one of these is higher? Well, the silver is higher, so the silver would be the cathode. Which one's lower? Well, the iron is lower. Oh, you guys, you know what? There was supposed to be like an electrode here that kind of got cut out of that picture. So the iron would be the anode, and then the silver was 0.8. The iron was a negative 0.44, and then I guess negative 0.8 minus a negative 0.44 is 1.24 volts. Now all of our questions have already been answered. We kind of just have to fill them out. Which element is gaining electrons? Well, it looked like that silver is gaining. Which element is losing electrons? The iron is losing electrons. Which one is being oxidized? Leo says Gur. Whatever's losing electrons is being oxidized. Which element is being reduced? The silver. Write the two half reactions. Okay, the reduction half reaction would involve the silver, and we need to make sure our electrons are on the left side of the arrow. So we would have Ag plus E minus goes to Ag. And then for the oxidation half reaction, the oxidation half reaction will always have the electrons on the right side, but if it's Fe2 plus, we would have Fe plus 2 electrons coming from that iron metal. And now technically, if you want these electrons to balance, I guess we have to double all of these here. So we have 2 electrons being gained, balancing out the 2 electrons being lost. Okay, so this kind of gets into the theory of what's going on in a battery. And then one more time, I want to get out all my kind of junk here, and let's check this out now. So I got a lemon here. I got a piece of copper, and what should I use here? I'll just get that iron. So I got a strip of iron here. Now I want to show you, without this lemon here, I have copper and iron. If we look on our standard reduction potential chart, you know, copper has a positive 0.522. That iron had a negative 0.44. You know, these are different, so they can create a voltage if we connect them. So this voltmeter is kind of serving as a wire, and when I touch these two together, can you read what I'm getting here? I'm getting 0. This is because there is nothing to allow charge to flow here. And that was the purpose of this lemon. So if I can stick, and I'm going to kind of, this is an old one, so I'm going to kind of get those juices flowing again. If I can get this copper in here, and I can get this iron in here, and there is any juice connecting these two metals, when I touch this together now, you notice that I am now seeing a voltage here created. Two metals stuck inside a lemon are creating electricity. Pretty crazy. Now in this example, and this is going to kind of help you for the lab we're going to be doing later today, which one of these metals would be the anode, which one would be the cathode? Well, just look again. What's the anode? The thing with the lower standard reduction potential. What's the cathode? The thing with the higher. So I have copper, which has a 0.52. You guys don't worry about which ion it is. You could just pick one and I don't care. Copper is a plus 0.52. The iron was a negative 0.44. So I guess copper in this problem would be serving as our cathode. It has a higher value. And the iron would be serving as our anode, the lower value. And why do we have a lemon? Well, the lemon is acting as our salt bridge, allowing charges to flow in a way. Okay, I hope this helps explain what a battery is and why these two metals stuck in a lemon are creating voltage.